Okay, let us get started with the Gram-Schmidt orthogonalization procedure for signals, and that concept should basically lead us to basically treating signals as points in the signal space, right. We just derived in the last module that the error in the reconstruction, the squared error in the reconstruction is basically the original energy in the signal minus the norm square of the signal whose components are basically these SKs in the signal space. So, we will basically first get how to get the basis is the first question, right, because once you get the basis, then you can represent them and then you can compute how good your representation is. So, we will start with an example, and I think you can now link the signals to vectors and basically invoke the same proof that you did for the Gram-Schmidt orthogonalization procedure for vectors. Now, let us start with an example. Suppose I think of these waveforms like this. S1 of t is 1 for capital T by 3 seconds, some time units. I have S2 of t which is for 2/3 of this time. This is 1, it is 0 otherwise. S3 of t is is 1 between capital T by 3 to capital T so many units of time, and we have S4 of t which is 1 for capital T units of time. So, if we just observe these signals under the definition of the inner product in the integral sense, right, you can figure out easily that some of them are orthogonal pairwise, but are they, are some of these linearly independent is another question that you might ask. But obviously, for example, if you consider S4, this signal here, right, S4 is basically S1 plus S3. Which means that in this signal set that I have S1, S2, S3 and S4, some of them are linearly dependent, right. The question is, can I construct an orthonormal set? For these signals, and these type of rectangular pulses sometimes in power systems etc., you find these with stepper motors etc., you find these step pulses coming through, right. And I do not know if one can think about an application of this signal representation problem in the power engineering space, but at least you can kind of relate to these type of waveforms that we see. They are not unrealistic waveforms. Okay. So, let us see how we can apply Gram-Schmidt orthonormalization procedure for signals. Exactly the same way that we did, you start with the first basis. So, I have S1 of t divided by the norm of S1 of t. This norm is basically 1, right. So, at least I am setting this to norm 1. So, this is S1 of t divided by square root of integral of S1 square t dt, right. So, it is pretty straightforward that this is root of 3 by t for this duration of time, and it is 0 else, right. You take the, you square it up 1 square. So, you just have root of t by 3 in the denominator, and you just flip it out, it is root of 3 by t, and S1 is 1 basically, and that is trivially 1, root of 3 by t times 1 for this interval 0 else. So, similarly F2 of t is S2 of t minus S21. This is basically the inner product of S2 with F1 on F1 of t, right. In you have to remove that component out, and if you want to normalize this, this is basically norm of now. How do you compute? So, now S2. So, if you take the integral of S2 with F1, you just with F1 you dot it, right. S2 with S of t, S2 with F1 in the direction of F1 is what we need to do, right. You can take the inner product, right. So, I would say S I j here in general is basically so basically if it is S21 is S2 of t, the inner product of S2 of t with F1 of t under this norm, under this definition, right. Sij is Si of t, Fj of t, and so S2 1 is S2 with F1, right. So, if you carefully did this math, so you just observe the signal. When I take S2 with S1, right, if you just observe this diagram, when I take S2 with F1, this exists only in 0 to t by 3, because from t by 3 to 2t by 3 it just does not exist, the inner product is going away. So, what you are left with the pi is basically this signal 0 to t by 3 defined from 0 to capital T by 3, right. 1 from 0 to capital T by 3, that is what you have for that pi of the signal. So basically when you subtract all these things and when you normalize, you will end up with root of 3 by t. So basically now you can think about when you subtracted it, S2 has S2 is basically the signal. When you take the inner product is what you get. When you subtract it, you will end up with basically the pi from T by 3 to 2T by 3, right. It is very straightforward. Right? This example is very illustrative, not much of math you have to do, just if you just see through the figures you can kind of imagine what they are. So basically this is from 1/3 of a time to 2/3. So typically this capital T is a signaling period in terms of signals. I mean for communication signals there is something called a signaling period for these pulses, and that is what it means in the signal processing sense, but you know for math you do not have to worry about it, some t seconds. Okay. So this is 0 else, and you do the math for F3 the same way. Take S3, compute the inner product of S3 with F2, then S3 with F1, remove those components out and just normalize the signal. It is just a routine trick that you will have to do. So this is basically, if you can guess, it is root 3 by t, 2t by 3. Zero else. Okay. So now we have F1, F2 and F3, and let us see how they look. This is my F1, my F2 is from 2t by 3 to t, and F3 of t is from 2t by 3 to t, this is root 3 upon t, right. This is how I have, and if I want to represent my S1, my S1 is basically 1. So S1, if you just recall, is this waveform which is 1 from 0 to t by 3, right. So this is S1t. Now this is basically, if you want to express it in terms of F1, this is basically root t by 3 times root of root t by 3 times root 3 by t gives you 1. So therefore this is square root of t by 3 in terms of the coordinate on F1, 0 component on F2, 0 component on F3, right. So you can think about this corresponds to F1, this corresponds to F2, this corresponds to F3. It makes sense because F2 and F3 have no components, and in F1 it is root of t upon 3 of F1, right. This is the coordinate representation for the signal S1. So, S1, which is this vector, is basically sort of, I would say it is equivalent to this. This signal is basically this coordinate in this space, and I think it is very important to get this feel. Just by inspection, if you observe, right, the support really there is no overlapping support for these F1, F2 and F3, right. That means F1 and F2 they are orthogonal, mutually all these F1, F2, F3 are orthogonal, and they are normal as well, I mean they are orthonormal, and because they are normal you can write them in this coordinate form, because you have to normalize the length, normalize. So, therefore, this normality is taking care, this root 3 by t is basically normalizing. It is very important to normalize. So, now you get a sense here. So, S2, this vector can be is so S2 is what? So, if we go through we have from 0 to t by 3 and then from t by 3 to 2t by 3. So, therefore, you have components from F1 and F2 as well, right. So, therefore, you have a root t by 3, a root t by 3, a 0. So, you can just do this and convince yourself. S3 is basically 0, root t by 3, root t by 3, and S4 has all these components. So, we are done, because this was the aim where we wanted to start with in the beginning of module 1, where we wanted to write signals as vectors, and indeed we have written signals as vectors. So, now these signals S1, S2, S3, S4, though I have given you 4 signals, they reside in a 3-dimensional signal space spanned by F1, F2 and F3. And now it is very easy now for you to figure out what is the angle between S4 and S3, what is the length of S3 or S4, everything you could easily figure out, right. So, the length and angle that we are used to in the vectors can be equivalently transformed or translated rather to the lengths and the angles for signals as well. So, the geometry of vectors can translate to the geometry of signals in the signal space. And now, since we have vectors, signal is transformed to a vector using this appropriate coordinate system. A lot of linear algebra can be applied to signals. Basically, it is now just vectors now. Okay. So, we are ending this module here.